CIA stands for confidentiality, integrity, and availability. These three principles form the core of cybersecurity and are commonly referred to as the CIA Triad. Here's a detailed explanation of each component. Confidentiality defined. Confidentiality ensures that sensitive data is only accessible to authorized individuals or systems. It is fundamentally about maintaining privacy and preventing unauthorized disclosure of information, both in storage and during transmission. Practical applications. 1. Access control. Access to information is restricted based on roles and responsibilities. Policies like role-based access control, RBAC, ensure that employees only access the data necessary for their work. 2. Data classification. Information is categorized based on sensitivity, e.g. public, internal, confidential, top secret. Controls are implemented to manage access based on classification levels. 3. User education. Employees are trained in security best practices to minimize risks like phishing, social engineering, or accidental data leakage. Awareness programs teach the importance of safeguarding sensitive data. Methods to ensure confidentiality. 1. Encryption. Protects data in transit, e.g. TLS SSL for secure web traffic, and at rest, e.g. AES encryption for stored files. Even if data is intercepted, encryption ensures it remains unreadable without the proper decryption key. 2. Authentication mechanisms, username and passwords. Basic level of access control. Two-factor authentication adds an extra layer of security by requiring an additional form of verification, e.g. OTP biometric. Biometric authentication uses unique biological traits like fingerprints or facial recognition for secure access. 3. Least privilege principle limits access to only what is necessary for a specific role or task, reduces the risk of internal threats and accidental misuse. 4. Data masking and tokenization. Sensitive information is hidden or replaced with placeholder values to minimize exposure. Common in scenarios like development environments or customer service interactions. 5. Monitoring and auditing. Logs and monitors user access to detect unauthorized attempts. Security information and event management (SIEM) tools can analyze and respond to suspicious activities. Examples in real life. Healthcare. Patient data is encrypted and only accessible by authorized medical professionals. Banking. Two-factor authentication secures online transactions and account access. Software development. Java developers access source code but do not have access to employee personal records stored in HR systems. Integrity ensures the accuracy, consistency, and trustworthiness of data throughout its lifecycle. It guarantees that data remains unaltered unless changed by authorized individuals or processes. Key principles. 1. Accuracy and consistency. Data must remain the same from creation to usage unless authorized modifications are made. 2. Unauthorized changes prevention prevents tampering or accidental modifications by unauthorized entities during storage or transit. Mechanisms to maintain integrity. 1. File permissions and access control. Restrict data access to authorized users. Examples: role-based access control, RBAC, multi-factor authentication, MFA. 2. Version control systems. Track changes and prevent accidental overwriting. Example: Git maintains file versions and change history. 3. Backups and redundancy. Enable data recovery in cases of corruption, accidental deletion, or attacks. Example: scheduled snapshots and replication in databases. 4. Checksum and hashing. Checksum validates file integrity after transmission. A checksum mismatch indicates data alteration. Hash functions, cryptographic algorithms, e.g. 26MD5, generate unique outputs for data. Even minor changes in the input data result in completely different hash outputs. Example: websites often provide checksums for software downloads. Users can calculate the checksum of the downloaded file to ensure it matches the provided value, verifying its integrity. 5. Data validation ensures inputs conform to expected formats to prevent corruption during processing. Example scenarios: network communication. TCP/IP uses checksums to detect and discard corrupted packets during data transfer. Software development. Hashes verify the integrity of source code files during updates or collaboration. Database management. ACID properties, atomicity, consistency, isolation, durability maintain data reliability. Availability ensures that systems, networks, and data are accessible to authorized users whenever needed. It focuses on minimizing downtime and disruptions while ensuring reliable access to resources under all circumstances, whether routine or during attacks or disasters. Key components of availability. 1. System and network uptime ensures that hardware, software, and services are functional and accessible to users. 2. Recovery from disruptions, quick restoration of services in case of failures, attacks, or disasters. 3. Resilience against attacks, protecting against threats like denial of service, DOS, or distributed denial of service, DDoS, attacks that aim to overload resources. Techniques to maintain availability. 1. Regular maintenance. Perform hardware repairs, replace faulty components, and ensure optimal performance of devices. Keep operating systems and applications updated with the latest patches. 2. Backups and redundancy. Use backup solutions to restore systems and data quickly in case of failure or corruption. Implement redundant systems, e.g., RAID storage, secondary servers, to ensure failover mechanisms. 3. Disaster recovery and business continuity planning. Develop disaster recovery plans to quickly resume operations after natural disaster, power outages, or man-made disruptions. Test and refine these plans regularly. 4. Mitigating downtime risks. Load balancing. Distribute traffic across multiple servers to prevent overload. High availability clusters. Ensure services remain accessible even if one node fails. 5. Protection against attacks. Firewalls and intrusion prevention systems, IPS, prevent unauthorized access and block attacks. DDoS mitigation tools. Use solutions like web application firewalls, WAF, and anti-DDoS services to detect and block resource overloading attacks. 6. Monitoring and alerts. Use network monitoring tools, e.g. Nagios, to detect and resolve issues before they escalate. Implement real-time alerts for potential downtimes or system failures. Denial of service, DOS. Attacks. A DOS attack overwhelms a system, making it unavailable to legitimate users. Common methods include flooding servers with excessive requests, exploiting vulnerabilities to crash services. Distributed denial of service amplifies the attack by using multiple compromised systems, botnets. Tag real-world examples. 1. Web hosting services. Redundant servers ensure that websites stay online even during maintenance or heavy traffic. 2. Healthcare systems. Hospital networks require high availability for patient records, medical devices, and communication. 3. Cloud providers. Providers like AWS and Azure use distributed data centers and backup power to maintain uptime.